It's my privilege to introduce to you our first presenters today on Clang, libc++, and the C++ standard. We have Marshall Clow from Qualcomm, a member of the library working group, and Richard Smith from Google, who is the project editor, meaning he runs the document. Take it away.
Thank you. As Paul said, my name is Marshall Clow. I work at Qualcomm in San Diego, and I'm responsible for libc++ in the LLVM project. And I also am the chairman of the library working group.
And I'm Richard Smith. I work at Google. I am the code owner for Clang, and within the C++ committee, I am project editor, which does mean that I produce the new standard drafts. I'm also an active member of the C++ core working group, which means that I have input on the core language features as they go past the committee.
And today we're here to talk about how the changes to C++ language and library are going to affect Clang and how Clang is going to implement them. Hello. Maybe.
Maybe.
Let me just try this. There we go. Okay. Now it's working.
All right. So we think it's good to start with a brief description of the history of ISO C++, just to give you an idea of how we got to where we are and where we are now. So the first ISO C++ standard was released in C++, it was C++ 98, released in 1998, after a long period of pre-standard C++ and various implementations of various levels of conformance to the informal spec as it was then. After C++ 98, the next release of anything resembling a C++ standard was in 2003, when there was Technical Core Addendum 1, TC1, which was effectively a set of bug fixes for C++ 98. It didn't introduce any big new major features. And C++ was then re-released as C++ 03, but for most purposes, C++ 03 and C++ 98 are the same language. Then in 2007, the C++ committee produced Technical Report 1, which was a set of library extensions in an experimental stood TR1 namespace, which was out there for experimentation for determining whether these features should go into the next C++ standard, which at the time was C++ OX. And the idea was that would be released in 2008 or maybe 2009 with the selected parts of TR1. But as you can see, we didn't get a new C++ standard until 2011. And since then, we've had C++ 14 in 2014, and we're looking at C++ 17 in 2017. But between C++ 98 and C++ 11, we didn't really have any substantial new C++ standard. And that's a really long time to have no new standard.
So, the after C++ 11 was released, the C++ committee got together and talked about how we could prevent having a dozen years go by again before having a standard release, realizing that that's not really fitting into the world we live in today. And we have gone to what's called a train model, or what we choose to call a train model, which is basically regular updates to the standard right now it's every 3 years. And basically, people work on things. We work on things in parallel. We put things into the standard. We set them into technical specifications, which progress independently of the standard. And every 3 years, we package up the things that we deem are ready to be incorporated into the standard and ship them. So the first one of these was C++ 14. And we had some contentious meetings about whether or not things were ready or not. And basically, we picked a bunch of stuff and shipped it out as C++ 14. The next one is we're hoping to be C++ 17. And we're in the middle of deciding what things are baked enough, what things are ready enough to go into C++ 17. Part of the problem with this is that the serialization process the standardization process is attracting a lot of attention. We have more and more participants. The last several meetings, we've had more than 100 people show up at the physical meetings. And the last pre-meeting mailing of things to consider at the meeting was the largest ever. I believe it was, what, 160 papers, something like that?
160.
160 papers that were dropped on everybody's doorstep 2 weeks before the meeting, and everybody had to read them and hopefully have opinions about them. Also, the last meeting, we increased the size of the standard by about 10%, and that's kind of, what's the good way to put it, kind of misleading, because this was the meeting where we were taking all this parallel work and merging it back into the standard. So this is a huge number for what we usually have. Anyway, there are lots of new exciting features on the way but coming down the road for C++ 17.
All right, so what we're going to be talking about today is a rundown of those new features in C++ 17 and maybe a few C++ 14 features that we think are interesting as well. We're going to be talking about the new building blocks that C++ 17 gives you in order to construct your programs in a more direct and elegant way. And we're going to be talking about how switching to C++ 17 will improve your existing code, possibly without you even having to modify it. For each of these features, we might talk about the impact on the language and the library, how those two interact with each other, and we'll mention the implementation status in Clang and libc++ of the features, so you know whether they're ready for you to use or maybe whether you should be thinking about contributing patches if you find them exciting.
So Richard mentioned building blocks, and I think this is a really important thing. The purpose of the standard library and the changes that are going to the language are to provide you and other people who are writing code in C++ better tools for building your programs. Basically, I call this walking up the abstraction ladder, that you get to spend more time concentrating on the things that are specific to the problem you're trying to solve rather than building fundamental infrastructure, because the language or the library will provide it. A real simple example of that is you say, oh, I need a hash table to implement my whatever. Well, you just use the hash tables that are in the standard library. You don't have to spend some time writing your own hash table. There's a perfectly good one there, and you can concentrate on the problem that you are looking to solve. So first one of these is the file system library, a file system TS, I should say. This is a specification that has been worked on mostly by Beam and Dawes for a long, long time. It was a part of Boost for probably the last 10 years. It has gone through several iterations. And this was the first of the TSs that we opened post C++ 11. TS stands for Technical Specification. Just an aside, Richard talked about TR1, which was a technical report. Sometimes I think ISO likes to change their acronyms every few years just to make sure that nobody is quite sure what's going on. But they're functionally the same thing. Anyway, the file system library provides OS-independent ways of traversing directory structures and getting and setting permissions and searching and so on. And it has been very popular as part of Boost, and now it's going to be part of the standard. Our status in LLVM is we have an implementation that has not yet been landed in the libc++ source tree. It's undergoing testing and review right now, and it should ship as a part of LLVM 3.9. Okay, the special functions, the mathematical special functions have this long and strange history. They were a part of TR1. Okay, they're a set of mathematical building blocks, basically. Again, this is building blocks. That people who do physics or mathematical programming use all the time, and people who do this are very interested in having a portable way to refer to them. Anyway, this was part of TR1, but we're decided that possibly the audience for this was not large enough to put into the standard, and so they were not part of C++ 11. They were spun out into their own international standard. Fast forward 5 years, and it has become clear that there is a large enough audience to put these into the C++ standard, and they will be part of C++ 17. The libc++ status is, this is a large job. We have not begun this yet. This has been estimated as a couple man-years worth of work. So if somebody is really interested in this, I'm looking for volunteers.
All right. Something else that's been worked on for C++ 14 and C++ 17 is lambda expressions. So these are a wonderful building block for kind of the low-level parts of your code where you want to pass a function to some other function, you want some elegant way of expressing that. And so they give you this, this nice terse syntax for expressing that you're passing a callable to a function. But they're kind of awkward for use in generic code in the C++ 11 form. Because you need to specify the types of the parameters. So here we need to specify something here and something here. And this is supposed to be a generic function for reverse sorting a container that calls sort and passes in a comparator that sorts using greater than rather than less than. But how do you write the lambda? Well, there are some unwieldy options. You can use this decal type construct or this type name construct, but these are terse, these are error prone, and it violates the point of lambdas, which is that they give you a really brief, simple way of expressing notions like this. So C++ 14 adds generic lambdas, which is giving us another place where we can use the auto keyword to mean deducer type, as it means in normal variable declarations in C++ 11 onwards. C++ 14 also lets us use auto as the return type of a function, which gives you the same type deduction of the return type that you get from lambdas in C++ 11 onwards. So notice we don't anywhere say what the return type of this function is, but the compiler figures out that it returns bool. And the way this auto works is it gives you an implicit template operator parens in the struct type, the closure type that's generated for the lambda. Another nice thing that we get with lambdas is we get this ability to capture by reference. The idea of capturing by reference is you don't make it, so when you have a lambda expression, it generates a closure type, which is like a struct type generated by the compiler based on the lambda expression. And the captures are notionally fields inside that struct type. When you capture by reference, you're capturing sort of a pointer to something outside the lambda. And one of the optimizations the C++ committee intended for that to be possible with that is that you can hold a pointer to the stack frame instead of holding a pointer to each of the variables you capture by reference. And to date, I think no one has implemented that because it has some severe ABI problems. For instance, if you do this in an inline function, then the caller's frame layout becomes part of your ABI, and no one wants that. So that there are some cases where you can do it when your lambda appears in a function that's not inline, and due to recent LLVM changes, we have these local escape and local recover intrinsics now. We think it's now possible to implement this. So that's something exciting that's coming, although it's not really a C++ 14 or 17 thing. Another thing you can do with captures is you can capture by copy. But there's sort of something missing here. If we can capture by reference, we can capture by copy. One of the great things that C++ 11 introduced was move semantics, and C++ 11 didn't provide any way to capture by move. So in C++ 14, we fix this with these things called init captures, where you get to say that inside my lambda, S refers to something which is bound to the result of this expression. So you take the string parameter, you move it into the capture, and then inside this S refers to the thing moved from the outer S. So you get this fully general syntax where you can capture any expression, not necessarily just this one, but it supports the ability to capture by move. And then C++ 17 gives us another facility for captures. So in C++ 14, you can capture by reference or by copy for anything other than the this pointer. And the this pointer is always captured as a pointer. So if you have code like this, which is going to take a string and then at some point later run a lambda by enqueuing it into a thread pool, and it's going to call some function which actually happens to be a member function of your log message, you may have a problem. By the time this gets run later, maybe your log message has been destroyed. So C++ 14 doesn't provide you with an elegant way to solve this. You can explicitly capture your starless object as a separate named value, but then you need to remember to update this log call to run on that capture. And if you get it wrong, then you just get it wrong, and you're in hot water. What C++ 17 lets you do is it lets you say, I'm going to explicitly capture the surrounding object by copy. And so this call to log inside a lambda created like this will refer to a copy of the surrounding object that's been copied into the closure type. And you might notice there's something missing here that in C++11 we had captured by copy, C++14 that's us captured by move. We don't have a way of capturing star this by move. And so I expect there'll be more extensions here in the C++20 timeframe.
Thank you. So one of the things that was added to C++17 was, well, one of the projects that was moving in parallel to C++14 and 17 was the Library Fundamentals Technical Specification. And this is a group of facilities that were library only, and many of them have been moved into C++17. So we'll talk about a couple of them. We'll talk first about stringview, because it seems to be the most popular. It's a very useful one. It is, the best way to describe it is a non-owning reference to a contiguous sequence of characters. So it's a container that doesn't own its own storage. It's basically a reference to some other, or a view onto some other piece of storage. The good news is that this is really, really useful. There's lots of cases where people have a chunk of text and they want to refer to a piece of it. This grew out of some work in LLVM and at Google, where, to no one's surprise, they have lots of projects that deal with large chunks of text that they do not wish to change. They merely wish to parse or to understand. For example, in LLVM, you read a source file in, and then you start parsing it, and you start pulling pieces out of it. Well, you don't really pull the pieces out of it. You merely pass references to the chunks of these around. Anyway, stringview has almost the same interface as a constant std string. Okay? It's pretty much a drop-in replacement for a constant std string, but is much cheaper to construct. Constructing a temporary string is expensive. You have to allocate memory on the heap. You have to copy the characters into this. The first one of those is usually the most expensive. Allocating memory is expensive. To construct a string view is very cheap, because really conceptually it is a pointer and a length, and that's all it is. Anyway, so you should consider, if you have a bunch of string processing stuff where you don't actually change the underlying string, you should think about using stringview. There's two caveats here. The first one is because string views do not own their storage. There's lifetime issues there. You have to make sure that your string view does not outlive the object that actually holds the text. And the second one is that string views are not necessarily null terminated, and that has bitten a few people. Another building block that we added in C++17 is this concept of basically searchers. The algorithm in C++11 and 14 called std search is basically, you give it a pattern and it searches for a match there, and it is unspecified how this works. And most implementations are very straightforward. It does pretty much what you think it is. It looks for the first element, and then this is, does it match? Nope. Okay, moves on, looks for the search element again. This implements basically a pluggable framework for searchers, where you can choose the search algorithm that fits your needs. And the initial implementation includes Boyer-Moore and Boyer-Moore-Hochspool, which on some patterns, especially where you have a fairly long pattern that you're searching for, can be dramatically faster. Anyway, the status in libc++ is that this is complete. Whoops, I skipped that in the last slide. For both stringview and the searchers, that this is completed in the library fundamentals TS, so it's a std experimental whatever, and will be merged into the standard namespace very soon.
Okay, so another one of the fancy things that we got back in C++11 was generalized constant expressions, which allow very sophisticated compile time calculations to be performed. You can build lookup tables, you can declare global variables and compute their initializers at program startup. It's a wonderful feature, but in C++11 it was very limiting. You were restricted to having no mutable variables. There could be no control flow in your calculations. and you're forced into a very awkward functional programming style involving lots of recursion. So here's an example of a C++11 const expr function that's just trying to determine if a null terminated string contains a character. And so we can see that we need to do some checks and use a ternary rather than an if-then, because we can't have actual control flow. And we need to force this all into a single expression, because the format's got to be return and then a single expression. And then we finish with a recursive call, because in C++11 const expr, the only way to get anything done is to recurse. And it turns out that even with those limitations, this is still Turing complete, but only just barely. And if you want proof of that, then in Clang's test suite, we have a test case which emulates a Turing machine in C++11 const expr. It's kind of a hairy mess, but it does work. And we also have a solver for the n-queens problem in there as well. Entertainingly, we've tested these two examples against MSVC and GCC and EDG and Clang. And of those 4 compilers, some of them get one right and fail on the other one. Some of them fail on the other one and get the first one right. But only Clang was able to handle them both. C++14 improves the situation here. Most of the restrictions on const expr functions are gone. We have an almost complete compile time function evaluation system. We can have control flow, we can have mutable variables, we can write in styles that are familiar to us, use the same code for compile time and runtime without worrying too much about maybe a performance hit of forcing our code into non-tail recursive form. There's lots of advantages of this. But it's only almost full compile time function evaluation. There are still some problems. So consider this rewrite of our contains function. We're going to use stringview instead. And we're going to use a standard algorithm instead of writing the loop ourselves, because this is the way that, that modern C++ gets extra composability. So we're going to use the standard algorithm anyOf to search the string view, and we're looking for a character that's equal to RK, and we're going to capture that implicitly by copy. But this doesn't work. And the first reason this doesn't work is that std anyOf is not actually a const expr function. It's not allowed to be used from constant expressions.
And there's a problem with that. So we are moving towards getting some of that fixed for C++17. It won't all get fixed. We just voted a bunch of more const expr stuff into the standard library so that many iterator operations are const expr, so that you can iterate over containers and so on. But and we have another paper we're reviewing about adding const expr to most of the algorithms. It's unclear whether or not that will get into C++17. But it's not a technical reason why most of these aren't const expr. We just haven't actually gone through and convinced ourselves that yes, these work and that they make sense. So that's where we are with those.
So the other problem with this example is that it uses a lambda expression, and in C++14 you can't use lambda expressions in constant expressions. It's an arbitrary restriction that we have left over from the C++11 days. One of the C++17 features that we're bringing in is the ability to use arbitrary lambda expressions inside constant expressions, and we think this is going to drastically simplify the programming model and make it much more natural to turn your existing computations into const expr computations when it makes sense. And as it turns out, you don't even need to write this function at all. Stringview has a const expr refined function which does this for you from C++17 onwards.
Okay. Another thing that was in the library fundamentals TS that has been recently voted into to C++17 is std any. Any is a container which can hold any type, a single element of any type. And this type can be changed on the fly at runtime. It doesn't have to be specified at compile time. This came from Boost, as so many of our library fundamentals tools did. It's been in Boost for a long time, since like 2003, 2001 actually. Basically, the idea is that you can put anything into an any object, and then when you get it back out, you get the same type out. This is really useful for interfacing with less strongly typed languages like, say, Python or JavaScript or whatever. But you can also query the any object to say, what type do you hold? And you get back basically a type ID, or type info pointer. And then you can do things based on what kind of type somebody has handed you. Anyway, status is, this again has been fully implemented and will be merged into the namespace STE soon. Variant, on the other hand, is not quite in the standard yet. There's a lot of interest in it. Basically, this is a type discriminated union. It's a better tool than the union that we got from C. You specify at compile time the types that it can hold, and you can put one of those into it, and you can ask it, what type do you have? But you can't use it, for example, for bit bashing the way people use unions. You can't put a pointer in and get a long out. That's what reinterpret cast is for. Anyway, it's not currently part of C++ 17. There's a lot of interest in putting it in. I expect we will see it either in the later version of the library fundamentals TS or C++ 17. We have begun implementing this for libc++. Optional. Optional, variant, and any are three very popular things in the Boost community. This optional, the best way to think of it is a container that can hold exactly 0 or 1 elements. It either has something or it doesn't. There's no multiple things. Swift has popularized this, interestingly enough. Swift is basically the Swift language has got first-class support for optional in it. Anyway, it's if you have something that might fail, for example, that you still want to return a value, but you want to return a value that basically says, yeah, there's nothing here. Frequently, if you have something that returns an int, you return -1 or something like that. But sometimes you need a special out-of-bounds value for this. Anyway, this is complete in the library fundamentals TS, and we will be merged in a namespace STD soon. Basically, when I say it's completed in the fundamentals TS, so it means you can use it today with libc++. You basically include experimental/optional, and you get it, and you refer to it as STD experimental optional. But soon it will just be stud optional.
All right. So I'm going to talk about a feature which is completely new in C++ 17. It's a new way of working with veryerotic templates. So veryerotic templates are a way of writing, for instance, a function template which takes any number of function parameters, like a C-style varargs function, but you can actually make it type safe, and it's going to get instantiated separately for each different number of parameters and for each different set of types of parameters. So this example is of a print function whose purpose is to print out all of its arguments, writing them to a cout with spaces between them. And it's a veryerotic template function. It will print out its first argument followed by a space, and then print out the rest of them. And this stood forward as just perfect forwarding magic, which C++ likes you to write for these cases. And then we have a base case for the case of exactly 1 element where you don't get a space. And it's kind of awkward to have to write this recursion. And fold expressions give you an alternative. And what they let you do is they let you say, I have a pack, and I have a binary operator, and I want to join the elements of this pack together with the binary operator. So, for instance, one thing you could try is you produce your cout expression, and what you actually want is, well, this isn't quite what you want because it doesn't have spaces in it, but what you want is something like cout left shift t, left shift, each element of this pack, t's in turn, t0, t1, and so on. And you write that using this syntax where you say, I'm going to have something, and then left shift all the elements of t's one after the other. This doesn't quite get us what we want because it doesn't put the spaces in, but it demonstrates the general idea. And we can actually solve the print problem using a fold expression, but using a different operator. We use operator comma. Operator comma is a very unloved, underloved operator in C++. It takes a bunch of expressions, it joins them together, and then it evaluates them one after the other. We generally only see this in the third condition of a for loop. It doesn't really appear in very many other places. But it's a general operator. And we can fold over that operator. And this time we're going to start by writing at RT, and then we're going to form this pack of expressions from our pack T's. And the first expression is going to be cout left shift space left shift T0. The next one is cout left shift space left shift T1. And then we join them together with commas, expand the pack, and we get this sequence of cout lines, which does exactly what we want. And Clang has supported this since version 3.6.
So in C++17, we also added support for this into the library using the big fancy names conjunction and disjunction, which are, again, fancy names for and or. And so now you can take things, you can take compile times expressions and a whole bunch of them together to get a single answer. This was able to be done before, as Richard said, with a set of templates that, a base case and a veryerotic case. But now you can just say, this is an example, all arithmetic. Are all of these types arithmetic? And you say conjunction is arithmetic T ... And so you static assert that int, float, and short are all arithmetic. Yes, they are. Int, void, and short, not so much.
Another new feature that's coming in C++17 is a feature called constexpr_if. This is a feature which lets you write a function template in such a way that parts of it are selectively not instantiated. And the reason you might want to do this is if you have some part of your function template that only works for certain forms of template arguments. So we can look at our example print from a couple of slides ago again. The reason we needed a base case before was because if you only have one argument and you only have the veryerotic template, it's going to try to recurse calling print with no arguments, and there is no such print, so that will be an error. And we can solve that problem using a constexpr_if as follows. We have the recursive call inside this if constexpr check that we actually have additional arguments to print. And then because that's not instantiated in the case where our pack T's is empty, we never see an error because this is calling a function that doesn't exist.
So this also simplifies the implementation of generic code quite a bit. You can do things like this. You can write a function that takes a pair of iterators and write separate cases for different capabilities of the iterators. For example, if you have a random access iterator, let's just say this munge was a find. You were looking for a value and you knew they were sorted. Okay, if you have a random access iterator, you can do binary search and narrow it down quickly. But if you only have forward iterators or bidirectional, you have to start at the beginning and move on and just look for the first one. The previous, in the current language, the way you would do this is you would write two separate functions that did things different way, and you would bracket them with enable ifs or use tag dispatch to choose at compile time which one you wanted to actually instantiate and call. This way you can share common code, you can keep them together, and it makes the code easier to understand and hopefully shorter. Type traits. The library has gained an awful lot of type traits in C++ 14 and 17. Basically, if you're not writing generic code, you're writing what I call concrete code, where you know all the types you're dealing with, in which case these type traits are not going to be that interesting to you. But if you're writing generic code that is designed to work with a bunch of different types, sometimes you need to know details about the type. Example here, this is the classic example, is vector pushback. Okay, std vector pushback, when the vector's full, what does it do? It allocates some new memory, copies, somehow transfers everything over into the new memory and deallocates the old memory. Okay, that's how vector works. That's how it gets the linear amortized time. But how does it move stuff? How does it transfer stuff to the new area? Well, it uses the type traits to see. If the type is trivially copyable, it's an int. It's what we used to call pods, plain old data. It just calls memcopy, picks up the bits and lays down the bits, and it's done. Very simple. If the type is is move constructible, specifically if it's a no-throw move constructible. And there's a long story about why no-throw that I'm not going to go into right now because, well, this is a 50-minute talk, and I could spend 50 minutes talking about that problem. If it's no-throw move constructible, then what happens is it move constructs into the new memory, leaving the shells of the old discarded objects behind. And otherwise, it calls the copy constructors to copy them one by one. Important safety tip, if you have objects that you're putting into containers and you want them to perform well, make them no-throw move constructible. Oops, I had a note here. Anyway, for library type traits, we also have added variable versions of these. Basically what a type trait is it's a template that has a static member called value, which is a Boolean usually. But for some of the type traits, it's like a size t or something like that. For example, well, isArray, you pass it a type, it will tell you true or false, is it array? Rank, you pass it an array, it will tell you how big the array is. So that would be not a Boolean, but it would be a size t, 0, 1, or 2. Rank of int 3 is 3, for example. But we have added, for every type trait, we also added a variable called isFoo_v. So isRankV is just the value 3. And this makes it much easier to read because you don't have to say da-da-da, colon, colon, value all the time. This is very similar to the underscore t that we added in C++14 for all the traits that return a type. Oops, I'm not going to talk about it. We'll go on to the next one.
Okay, so another brand new feature we're getting in C++17 that people have been asking for quite some time is that we can now deduce template arguments from initializers. What I mean by that is, suppose we're constructing a tuple of 3 elements. And we're going to give it an initializer which says, here's the first value, here's the second value, here's the third value. Right now, we need to additionally and redundantly say what the type of those 3 values are. Or we can write a makeTuple function that will produce that type and then use auto on the left-hand side. But we need to write that make function ourselves. And it's kind of an awkward syntax for that expression. And so the new feature that we're adding is the ability to deduce these types from the initializer in a very general way. And we're also using toString here, which is another new feature in C++17. So the way that this works is you can specify for your type a deduction guide, which looks like this. It looks a bit like a function with a trailing return type, except there's no auto over here. So we say, when we're constructing a tuple from some sequence of types, the type you get back is a tuple of that sequence of types. And you can perform an arbitrary mapping between the types of the arguments and the type that you get out. It's a very general feature. Another thing we're discussing doing is inferring these deduction guides from the constructors of the class. So in a lot of cases, you wouldn't need to write any deduction guides. It would be completely automatic. And there are some cases where that works wonderfully, and there are other cases where it produces a slightly undesirable outcome. And so it's not completely clear whether we're going to go ahead with that or not, but we probably are. The feature in general has been approved by the evolution working group of the C++ standard. It's not yet been voted into the standard, but it has been prototyped in Clang. That's where the prototype implementation was done.
Thank you. So one of the things that that the committee has tried to do as we've marched from C++11 to 14 and soon to 17 is that not only to minimize the amount of breakage for existing code, goal would be none, but also to make existing code perform better. Give people, the compilers, the freedom to make optimizations that they were previously unable to do. In C++11, we got move semantics, which you can write code to help the compiler do less work for your thing. But the other thing we got was we got an implicit move for the return value. Basically, if you what was then called return value optimization or named return value optimization, where the compiler could elide a copy if the circumstances were right. But in C++ 14 and C++ 17, we got a lot more of that.
Right, so one thing we got in C++ 14 was the ability to optimize allocations and deallocations performed with new expressions and delete expressions. And there are two different optimizations that are explicitly permitted. One of them is that if you can see the start and end of an allocation, you can see the new expression and the delete expression, then you're allowed to elide both of them and create storage on the stack or possibly get rid of it entirely. And this is something which LLVM has actually been able to do for quite some time. It can do this for malloc and free, and it's been able to do this for operator new and operator delete, but that used to be a non-conforming optimization. And the reason it's non-conforming is because C++ lets you replace the default allocation deallocator, and so it's an observable effect if you change which allocations and deallocations happen in the program. And the change that was made to the language standard was to say, in the case where you're using a new expression and a delete expression, you're not allowed to care whether an allocation or deallocation happens. This requires some changes to LLVM to accommodate it, because not all calls to operator new and operator delete get the special behavior of being optimizable anymore. The way we implement this is we have the ability to declare a function that would normally be considered to be a built-in as no built-in. And then on particular calls to it, we can say those calls have the built-in behavior, and then all other calls do not. And it's important that it's that way around because, for instance, a call through a function pointer that can then be reduced to a direct call would inherit the value from the declaration. And this extends to the standard library as well. We've changed libc++'s std allocator implementation to use the new semantics, and the way it opts into those, because it can't actually use a new expression and delete expression for boring technical reasons, is we add a built-in operator new and built-in operator delete function, which give the same behavior as the new and delete expressions. So these are optimizable calls to operator new and operator delete. And this means that we get to optimize everything that uses std allocator, so vector and map and std list and all these other things get this optimization as well.
String.
And string.
String.
Another thing that gets better in C++ 14 is we get to optimize deallocation in the case where we statically know the size of the object that's being deallocated. And what happens there is the compiler passes the size of the object to the deallocator in the case where it knows it. And this, for some allocators, allows you to deallocate more efficiently. It allows you to go directly to the right pool to return the memory, which means adding these functions to the library, which take a size t in their operator delete, which says the size of the deallocation. Unfortunately, we've had some problems with this in Clang. The biggest problem we've had is that these functions should live in the C++ ABI library, and they're going to be implicitly called by existing code if you just turn on C++ 14, which means that just by changing that language flag, suddenly your low-level C++ ABI library needs to have a newer ABI. And that's a problem on a lot of distributions. It's something that we can't just tell people overnight, switch to this, because while we do have an ABI library in libc++ ABI, we also support people using other ABI libraries which may not have this functionality. And I think GCC maybe 5.3 added these. So if you're using a new enough GCC or you're using libc++ ABI, then you can use these things. And if you want to, you use the -f size deallocation flag, but it's disabled by default in Clang. And finally, C++ 17 gives us some performance advantages as well. So in a case like this, a lot of temporary objects are created by C++. There are, in fact, 4 temporary objects here, which I've highlighted in red. We create temporary strings from these string literals. We create a temporary string in the result of operator plus, and we create a temporary string in the result of f. So that's 4 additional strings, each involving at least a move and, in C++ 11, a copy. But even when it's a move, it's not free. In practice, since C++98 compilers have been allowed but not required to elide these copies, but due to the model used by C++, the temporary objects are created immediately and the copies notionally exist. And so even in the cases where you do get the performance benefit of the copies being elided, it's not a portable performance benefit. And if these are large objects just directly, then you can still see some problems there. What C++17 does is to change this model to say, don't create the temporary objects immediately, wait and see the context in which the expression is used. And if it's used in a context where you're going to be initializing a variable from it, then don't create the temporary at all, just directly initialize the variable from the initializer that you would have used for the temporary. And so in this case, all of the temporary objects are gone. And actually, in Clang's implementation of this, making this happen requires turning off parts of Clang's code. The parts that would create the redundant temporaries are just disabled to allow this. As an aside, if you use stringview instead of string here, you can get rid of 2 of the 4 temporary objects. So that's another thing you might want to keep in mind for performance.
Okay, we're a little bit short on time, so I'm going to run through these next slides fairly quickly. We talk about, there's been a lot of controversy since the last standards meetings about things that are not in C++. And this is a feature of the train model. Things that that the committee thinks are not quite ready, not quite cooked. Trains leaving the station, they're not going to be there. There's a lot of people on the committee who believe that having regular releases is much more important than having large featureful releases, especially after C++ OX, OA, OB, oh yeah. The OX means it's hex, right? Because it's still in the 2000s if it's before 2016. But anyway, big upcoming features that are not in C++17, concepts and ranges, coroutines, modules, networking. We'll run through these real quick because we are at like 7 minutes left.
Okay, so concepts are a way of constraining templates to express your desires for what your template parameters should be. So usually when you say template type name T, you don't really mean any type T. You really want to specify some sort of kind there, some sort of way of saying this collection of types is okay, that collection of types is not really what I'm looking for. And concepts is a way of doing that. It allows you to specify a concept which is a predicate over a type and use that as a template parameter in order to improve the diagnostics you get when you use the wrong type. We can immediately say when we see the instantiation, hold on a second, you said you wanted an iterator, this thing you've got here isn't an iterator. The other advantage of it is it allows you to directly express your intent with regard to how you structure your templates. You get to be very direct in saying what sort of thing you want to be passed to you in code rather than in comments.
So here's a concrete example. We have min. Min requires of this type T that they be less than comparable, where less than comparable is some concept that is defined elsewhere. But basically, if you get past something like complex here, 2 complex numbers, that it'll say, complex numbers are not less than comparable, which is exactly what you want to know. Anyway.
Yeah, so the C++ committee thought that the concepts proposal is not quite ready to board the train just yet. The syntax is a little bit too experimental. It's got lots and lots of different syntaxes for expressing function templates, and it seems overkill to have so many different syntaxes. And the syntax for declaring concepts is a little unclean. And there are some semantic problems. There is one particular algorithm involved for determining which of a bunch of templates is better than the others. And it turns out to be exponential time due to the way it's been specified. So we think it's not quite ready yet. And the users of concepts within the committee, most of them said they love the feature, it's great, we really need it, but they too want just a little bit more time for it to bake, for it to become ready. And so we expect concepts will be in the next C++ standard after C++ 17, which is probably going to be C++ 20, although there's some talk of doing a C++ 19 instead.
Okay, ranges. Ranges are another thing that has generated a lot of interest. The basic abstraction in the standard library between the containers and the algorithms is the concept of an iterator. Ranges is a different abstraction. It's, you can think of it as a pair of iterators fused together, but basically it's a collection of data that you can iterate over. The ranges proposal is based on the concepts. I won't say much more about this, but if you go and watch Eric Niebler's C++ Now keynote, C++ Now or CPP keynote about ranges in the standard library, you will come away with quite a bit of appreciation for it. He takes a simple problem and approaches it from a very different angle using ranges, and at the end of it has a very nice little program that is completely unlike how you would have attacked this problem before.
Another really great thing that's coming down the pipeline is coroutines, which it basically gives you first-class support for resumable functions where you can suspend your function at some point when you're done doing whatever it is you want to do and then be resumed later. As an example, you can write generators which will run for a while, produce a value, suspend themselves, and then be resumed the next time the caller says, I would like another value from you. This is very much like generators in Python. You can also use the same technology to implement futures. So for instance, you can write asynchronous networking code where you write in a very procedural style, but every time you get to a point where you would need to block, you use coawait, and coawait says suspend until this thing is ready, and then when it's ready, carry on running from here. And so we can build a function that reads, say, the LLVM website homepage, and very, very simply. So the model used for this, just very briefly, the function signature says how the coroutine is supposed to work. And typically it's the return type of the function that's used. It specifies what the different syntaxes mean, what coawait means, what coyield means, what coreturn means. And then the language gives you a way of saying, at these points suspend, and you get a handle to the coroutine, which you can use to resume it. Parts of the stack frame of the function are moved onto separately allocated storage instead. You get this opaque handle, which you can use to resume. And if you want to know more about the model, there is a paper here you can read for a specification. Clang supports parsing the syntax of this under a -f flag. We have a prototype implementation in LLVM due to Igor Nishanov at Microsoft. And he will be posting to LLVM Dev at some point soon with a set of intrinsics he wants to add in order to support this. The model there is essentially that you have a fork-style operation that splits your function into part that returns and suspends and part that continues. Finally, the last thing I'd like to talk about here is modules. Modules have been coming for a long time. It fixes a problem with textual inclusion for providing the interface of a library, which is brittle and slow. And it's a way of saying the interface of my library should be compiled separately and perform a semantic import at the point where you want to use the interface. And we have some concrete syntax for it from modules TS, which is nice because in the Clang implementation, we're using a transitional mode where we use the syntax from normal C++ without modules. We convert hash includes into imports. We have separate side tables saying where all the modules are. And having this explicit syntax lets us move forward to a much cleaner world. And we'll be implementing that syntax at some point soon.
Thank you. The last of the upcoming modules that TSs that people are working on is networking. This is based on Boost ASIO, which is basically a generalized framework for handling asynchronous I/O and other operations. There's a lot of work to be done here. This is the proposal in the TS is just a start, but there's a lot of power here and a lot of interest. The libc++ implementation, I've begun it. It's very early days still. Anyway, these pages are give you you can go and find out what the current up-to-the-minute status of libc++ 17, our C++ 17 implementation is, both in libc++ and in Clang. There's lots of work still to be done. The TSs are large bodies of work, some of which we have fairly robust implementations of. Others of them, not so much. So if you have a hankering to talk about, to work on these, please drop me a line or drop Richard a line. Basically, I got started working on libc++, implementing basically all the C++ 14 features.
And I got started in Clang implementing C++ 11 features, so it's a really great way to get started. All right, we'll now take questions.
We have 2 microphones set up. If people want to ask questions, you can queue up. If you're stuck in the middle of a row, we'll deal with it somehow.
Wow, I did not realize we explained things that well.
We've got a couple coming up.
One question that's triggered by, for example, some of these math routines that you want to add. Is there some thought of coordinating with the C standard? Because so far, I mean, the math routines, for example, C++ offered were sort of the same as the ones that C offered?
I believe there was also an addendum published to the C standard containing the same functions. I don't think the C committee has decided to take that into a new standard. I'm not sure they're producing a new standard, whether that's their plan of action at the moment.
Actually, I believe that they have started work on a new standard just in the last 6 weeks or so. But for several years, this standard, my impression of the status of the C committee was, we don't see any need for a new standard at this time. I believe that has changed very recently, but I don't know what they're going to put in a new standard.
I would suspect, given that these are in C++ now, there will be additional pressure on them to include these in C as well.
When users will be able to define functions from the STD namespace, like STD hash, because for now they cannot do it.
Okay, so the question is, when will users be able to define functions in this STD namespace, specifically STD hash? So the answer is that users cannot define functions in the STD namespace at all. That's specifically forbidden by the standard. But the thing is that STD hash is not actually a function. It is a template. And you can specialize templates. You can specialize objects, instantiations of templates in the STD namespace. So what you do is you specialize STD hash for your type, and this is an object that has a function call operator. And you can do that today. It's slightly different from specializing, adding a function, but that particularly is legal.
Okay, I thought that's also forbidden, so it's cool.
Okay.
Hi, I'd just like to thank you, both Richard and Marshall, for implementing so many of the crazy new features that are coming. And I'd like to thank in advance anyone that's actually willing to come and contribute more features, because I really like to see C++ getting so much more fun to use.
Thank you.
Yeah, and I'd like to say that I'm very grateful to everyone who has contributed patches to implement some of these C++ 14 and C++ 17 features already. That's really awesome.
Indeed.
All right, thank you very much.
Thank you.
Thank
We
you.
have 5 minutes until the next session starts.